Swayam Prabha. Digital India. Educated India.
Hello and welcome back. So in this video we are going to look at radionuclide imaging, sometimes also referred to as nuclear medicine. So this will kind of officially conclude all the radiologic imaging systems that you generally would run into. Okay, so here's the overall content. We're going to look at the physics of this particular modality and briefly look at planar scintigraphy, SPECT and PET. These are the three different imaging modalities which come under radionuclide imaging or nuclear medicine. Okay, so what is the physics of nuclear medicine? Okay, so these set of imaging modalities that we are going to see, they are collectively referred to as nuclear imaging or radionuclide imaging, and which basically involves a radioactive substance being introduced into the body, and then you allow for some time for the body to take up these substances, right? So this is why it's this particular imaging modality is referred to as functional imaging modality, because the tracer actually interacts with the biology, right? There is a biological interaction between the tracer and the body, also so the physiological interaction, if you can call it. So which means that more than the anatomy itself, like previously we were looking at even with CT, MRI or ultrasound, you are mostly concerned with the structure, right? So you look at anatomical structures. There are different contrast mechanisms, especially in MR that you have seen, but in this case it's mostly this is functional imaging. Basically, we're trying to do what is called physiological imaging. Okay, and how do we do that? And it's accomplished by looking at variations in concentrations of the radioactive tracer. Okay, and that then the hypothesis is that the variation will indicate that something is wrong. So for instance, there is a isotope of iodine that is used for imaging. Okay, iodine is readily absorbed by the thyroid gland, so any radioactively tagged any radioisotope of iodine would normally go and get accumulated in the thyroid glands, which will give you an indication of how good those glands are working. Okay, so this is the one of the very simple examples of how you would use radio tracers, as they are called, for imaging purposes. Okay, so on the right, the picture shows a typical imaging system. So we have the if you can call it, we have the patient here, and then we have injected the patient with the radio tracer or the radionuclide, and it has gone and accumulated somewhere in the body, and it emits most of the time. In fact, all the time, the preferred choice of emission is gamma rays. So the gamma rays are basically high energy X-ray photons, right? You can think of it as similar to X-ray, high energy photons, and they are typically monoenergetic, since they have the single energy. So for instance, 140 keV is a typical energy. Okay, and outside the body we have a bank of crystals, collimators, and behind which there is a scintillator crystal. Scintillator crystal traps these high energy particles that are emitted, and there is a converts that into light, which are detected by photolight multiplier tubes or photodiodes. Now there is a big difference, between this and the other modalities that you have seen so far. It's just that you see the source, quote unquote, you can call it that, is actually inside the body. Okay, that's a big difference. So if you look at all the other imaging systems, there's usually a deposition of energy, either in the form of radio frequency, or in the case of MRI, or an X-ray source outside the body, or in ultrasound, basically sound source, right? Ultrasound source. So all these are outside the body, and then it travels through, and then we sense it outside again. So in this case, the source of radiation, that is whatever we are sensing, actually comes from inside. Okay, but we have injected it, and then the idea is to localize and measure it. Okay, so this is the typical setup for all radionuclide imaging, including scintigraphy, planar scintigraphy, SPECT or PET. Okay. So just to summarize again, the nuclear medicine, a tracer molecule, we call it a tracer molecule or radio tracer, is administered to the patient by intravenous injection. That is typical. And what is this tracer? It's basically a molecule carrying an unstable isotope, which is basically a radionuclide, right? And typically these isotopes emit gamma radiation, that is high energy photons, while at the same time being metabolized by the human body. This is what I meant. There is a physiologic imaging happening here rather than just the anatomical imaging. Okay, the gamma radiation emitted turns out to be proportional to the concentration of the tracer, and which can be then the emitted radiation is recorded, and based on the emitted mean photon count, we can estimate the concentration of the activity. So we are not exactly do the absolute concentration, but something known as the activity concentration, right? So it's not just the concentration of the substance itself, but rather something known as the activity concentration is what is measured. So activity concentration is measured. So this we can actually show using simple mathematics, but just to give you an example. So for instance, when you are doing X-ray imaging, basically let's say X-ray CT, what you are measuring is the underlying quantity you are measuring is the linear attenuation coefficient, right? The attenuation coefficient is what you are trying to measure. That attenuation coefficient is typically turns out to be proportional to the depends on the the atomic number, the density of the element, right? So in this case, what we are measuring, even though we will be counting the gamma radiation, the number of photons in the gamma radiation, the mean photon count is recorded typically. Using that, what is being projected as a mean photon count is something known as the activity concentration, which in turn gives an indication of the actual concentration of the radio tracer at that particular tissue location. So we will measure this as both as a function of position and time. Okay. So this entire system of all the systems that we have seen, like I said before, is known as functional imaging rather than anatomical imaging. Okay, so just a primer on radioactive decay. And so radioactive decay is the rearrangement of nuclei to lower energy states. So there are some nuclei which are inherently unstable, right? And these nuclei tend to go to lower energy states. Again, this lower energy states corresponds to greater mass defect. This is again comes from the physics of radioactive decay, right? So basically the sum of the the parts tends to be lesser than the individual sums, right? So if you look at the if you calculate the mass of the protons and neutrons of an atom, and then you actually measure the nucleus of the atom, so that weight tends there will be a difference. So that difference is known as mass defect. Okay, and so usually they try to tend to lower energy states which have greater mass defect. Okay, so but we don't have to worry about this right now. Just to understand what the root of the instability of these radioactive nuclei or radioactive atoms. Okay, so typically the parent atom, that atom that decays, is called the parent atom. It decays to a daughter atom which has a higher binding energy per nucleon. Okay, so the mass defect translates to something called binding energy. And so this binding energy will be higher per nucleon if when in the daughter atom. Okay, so that is basically a transition to a much so-called lower energy state or a stable state. Okay, so again these are the terms that go into describing radioactivity, right? Radioactive atom is said to decay when the nucleus is rearranged. So if you have some rearrangement of the nucleus in terms of its atomic number or mass number, then it's called a radioactive. It's called a radioactive decay, right? And there is also a terminology used which usually you will see is called disintegration. A disintegration is basically a radioactive atom undergoing radioactive decay. Okay, and usually this radioactive decay is accompanied by some release of energy, which is of course what happens in some cases, like the release of energy is in the form of gamma radiation, which we measure. Okay, so there are several types of radioactive decay. So we will look at two which are commonly used in nuclear medicine or in radionuclide imaging. Okay, so the one of the modes of radioactive decay is through positron emission. Okay, so in this case, what happens in the atom is that a proton transmutes into a neutron and a positron. Positron is nothing but the antiparticle of the electron, same mass of the electron, opposite charge. Okay, The mass number A does not change. So, capital A typically refers to a mass number and Z refers to the atomic number. Since the proton is transformed, the proton number reduces. Okay. These positrons combine with the electron. So, when these are emitted, they combine with the nearest free electron and they annihilate, and that ends up in the release of 511 keV photons. Okay. And this actually is used for medical imaging. So, this is what is used in positron emission tomography, because whatever you inject, the radio tracer you inject into the body for positron PET imaging, it actually emits positrons which then combine with the nearest electron and then release these 512 keV photons which are detected. Okay. So, this is one radioactive emission route which is used in positron emission. So, for instance, the example, one of the examples of positron emission is fluorine, disintegrating into oxygen. This is called the electron neutrino and the positron here. Okay, so it's called a beta plus decay. This is just for sake of illustration, right? So there are a lot of radioactive compounds or radio tracer which emit positrons and are found favor in, for instance, in PET. So one of them that you will come across often that is used is the fluorine, radioactive fluorine, and it's used as fluorodeoxyglucose, right? So what happens is that they'll replace the oxygen in glucose with fluorine, and then you inject into the body. So what happens is, typically the hypothesis is that tumors have higher metabolism, so they'll uptake, this is fluorodeoxyglucose, right? So they'll uptake the glucose much more than regular tissue. So a lot of the FDG that you inject will end up in the tumor tissue, but remember that the fluorine is a radioactive, this is the radioisotope fluorine. It will emit positrons, and then so you will be able to measure whether particular tissue mass is actually a tumor or not based on the accumulation of this radioactivity there. Okay, so this is just in a nutshell as a general principle of how you would do positron emission tomography. The other means of radioactive decay is gamma decay, also refers to as an isomeric transition. So the radionuclide is inherently unstable, but there is no transmutation. It just goes into a lower energy state by emitting gamma rays. Okay, and in the context of diagnostic imaging, about 100 to 600 keV, it's the same range. So gamma ray is nothing but high energy photons. X-rays are also high energy photons, except that they just correspond to different energy ranges. Okay, so this is one element which is the example which undergoes decay by just emitting gamma rays. So this particular kind of isotopes which emit gamma rays are mostly used in something called the single photon emission computed tomography. Okay, I think it's computed or computed tomography, either way you want to use it. But typically it's SPECT, S single photon P emission computed tomography. Okay, I think this is computed tomography. So it's usually acronym is SPECT. So in this kind of imaging systems, gamma ray emissions are used. Okay, so each of them will have a slightly specialized hardware. So we'll look at them briefly when we get there. Okay, so for instance, SPECT imaging, technetium is often used. Okay, this is used widely, for instance, even for bone imaging as well as cardiac imaging. So most of the imaging that is done with SPECT involves technetium. Okay, and technetium decays by emitting gamma ray photons. Okay, and the emission energy is about 140 keV. So how do you acquire data for radionuclide imaging? So just to summarize what we have seen so far, so this involves basically injecting a radio tracer into the body. The hypothesis is that radio tracer will go and accumulate preferably in certain regions corresponding to the pathology. Okay, and so that's why it's called functional imaging. And what you have to do is, but then of course remember it's a radio tracer because it is in actually, and I say radio tracer also means that it's in very small quantity. You can't inject a lot of radioactivity into a person. You will of course cause damage. So you have very, very small amount of radio tracer is injected and they accumulate, and you measure the emitted gamma rays, for instance for SPECT, or high energy photons, 212 keV photons in case of PET, or for instance, or gamma rays in the case of planar scintigraphy. We will see that in all three cases you just try to measure the number of photons which are exiting the body due to the emitted radiation, right? So this detection of the emitted gamma rays is accomplished using something called the Anger camera, or we also call it the gamma camera. Okay, the Anger camera is named of the person who invented it, Anger, right? It's the name of the person. So it basically consists of a collimator up front. We saw that picture of the illustration a few slides ago, and behind the collimator is a very large crystal, scintillation crystal, which converts these high energy incident gamma rays into visible light. Okay, and the visible light output is basically measured by an array of photomultiplier tubes or photodiodes. Okay. So a typical, for instance, what you'll see known as planar scintigraphy or even for SPECT is a large crystal, fairly large crystal connected to multiple photomultiplier tubes, right? So how does the scintillator convert to light? So it's basically through photoelectric absorption. So the scintillator absorbs the high energy gamma rays with photoelectric absorption. The electrons resulting from the photoelectric absorption travel through the crystal, and in their interactions with multiple electrons, they release energy in the form of light photons. Okay, so the imaging geometry is shown here. We'll have parallel collimator holes. Okay, so I have not shown the collimator holes here. You can see that something like this, a bunch of lead shielding kind of array which sticks out of the detector, out of the scintillator, right? It's much longer here. You can think of it like that. So the collimator holes are to make sure that the gamma rays that are hitting the scintillator come from a specific direction, right? So you can't have, for instance, if you can't have something from here hitting it, you will be stopped by the collimator. So everything only in a straight line hits it. So you are making sure that the measurements that you are getting come from a specific region of the tissue and not from everywhere in the body. Let's say you had no collimator, right? There's a lot of scattering of the emitted radiation also possible. So you won't be able to localize. So the collimators are help localize, and the other aspect is the Compton scattering can be disregarded. This is again from the energy point of view, right? Because the emitted gamma rays are 140 keV, let's say for instance, right? 140 keV, right? The Compton scattered ones tend to be slightly lower energy. So there are ways of disregarding those signals. So the Compton scattering is done away with. Okay. What is measured is the activity, right? Activity concentration, which is also denoted by A, not to be confused with the atomic mass number A. Okay. And of course, we also assume that the gamma rays are more energetic, which is true mostly. And what happens in the case of planar scintigraphy is just you will get a picture just like a X-ray projection. We will see that in the next few slides. Picture we had here. So I'll just 1 second. Let me just wipe this out. So I'm going to draw it on the other side so that it's easy. So if you have a collimator here, okay. So you have a bunch of, let's say, I'm going to draw with a slightly different color. You get a bunch of radioactive compounds here. Maybe different concentration, maybe same concentration. It doesn't matter. So the signal you will be getting, so the scintillator is here, right? And then you have a bunch of, let's say the photodiodes are here or the photomultiplier tubes are here, right? So the signal you will get, right, is restricted for particular, this collimator is restricted to this, let's say this projection on the body. But this is depth, right? So so you can be sure that whatever signal that you are measuring here, the number of, which is basically the number of, proportional to the number of gamma rays that hit this particular spot in the scintillator, they are all restricted to this very small cylinder of tissue inside the body. Okay. So but then depth, resolution is kind of difficult to do, and there is one more problem. There is two types of attenuation that happens. So for instance, in X-rays, there is only the linear attenuation, right? But here there is also an 1 over r square attenuation because radiation is emitted in all directions. Okay, so it's not like radiation is preferably emitted along the direction, along the towards the detector, right? So 1 over r square, there's a 1 over r square fall off in the flux of the radiation. Also there is an attenuation, the exponential e raised to minus mu, the depth. So those two are always happening when you do this radionuclide imaging. The other aspect is in X-ray, for instance, if you can two projections acquired 180 degrees apart are the same, okay, because the path traversed by the X-rays will be the same. However, here it's not true. So if you have, let's say, radioactive compound somewhere here, right? If you measure using a camera on one side of the patient, the activity or that you measure will be slightly different, will be quite different from the activity that if you measure it from the other side. That is, basically take a measurement from here, right? From this side, let me draw that properly. From this side, and then let's say you rotate the camera around the patient and you take a measurement there. So because there are two sets of attenuations, right? One is each one of them depth dependent, and 1 over r square is basically dependent on the distance to the camera. Okay, so this depth dependence, it comes from this d is inside the tissue, this is distance to the camera. So when you rotate the camera, both of them change. Okay, so there is a depth dependent attenuation and distance to the camera attenuation, both of them at work when you do this gamma ray imaging, okay, or radionuclide imaging. So but having said that, so we just for planar scintigraphy, the detector is translated across the body of the patient, and at each point you record the amount of gamma ray photons being measured, and in turn they can be related directly to the activity concentration or the number of disintegrations per second, if you can think of, that happens inside the tissue at every location. Okay, so this is planar scintigraphy. Okay, so planar scintigraphy, it's more simple form of nuclear medicine imaging or radionuclide imaging. It is very similar to projection X-ray, so where each pixel corresponds to a projection along a line. Okay, so the gray value which is measured by the photomultiplier tubes is proportional to the amount of attenuated activity along that line, right? But it has to be corrected for depth and distance from the camera. Okay, I'll explain this slightly more. However, these are functional images. So see, projection X-ray, very difficult to discern anatomy because you have multiple tissue types along the path of the X-ray, and they attenuate them differently, but you won't be able to separate them. But in the case of even planar scintigraphy, even though it is similar to X-ray projections, it measures the activity concentration, so you do get functional information. Okay, so for instance, technetium imaging provides information about bone metal metabolism because technetium MDP, this particular isotope, is absorbed in the bones preferably. Okay, so what we have to, so this imaging chain consists of a positioning logic. Basically positional logic is for figuring out where in the scintillator the particular gamma ray hit, because it's a single scintillator, right? There's a pulse site analyzer to reject the scattered radiation. Okay, and these together are used to put together, they'll be used to estimate the X-ray position of each event. So just going back to the other one that we talk about, which is closer to X-ray imaging, the reconstruction is closer to X-ray imaging, is SPECT. It's called single photon emission computed tomography. So what this requires, as the name implies, it requires a reconstruction. So planar scintigraphy does not require reconstruction. You just translate the camera over the patient and every location. So it's a fairly large area, so you will be able to get the entire body as you translate over the patient, and you will get a projection of the underlying activity onto the camera. Okay, here we want to reconstruct, so it's a computed tomography thing, so we have to reconstruct. So they requires the camera that can rotate around the body. Okay, this is very similar to what is called CT, acquiring a series of projection images, right, at various angles. Right? That's what I said, very similar to CT. By projection images, we mean here recording emitted gamma radiation at different angles, right? And it's usually recording emitted radiation along a line projecting on the camera face, right? That's what I showed you in the previous illustration, right? So you always are recording along a straight, like a cylinder, which is basically projected from the face of the detector, right? And SPECT requires tomographic imaging techniques, and it is typically, and most of the SPECT imaging falls under whole body bone imaging and cardiac imaging. Okay, once again here the problem is projections acquired 180 degrees apart are not the same. Okay, because as I said, there are two effects. One is depth dependent attenuation of the emitted radiation, also distance to camera will vary. Okay, and this of course typically used for gamma radiation emitters. So here SPECT, once again, it's very similar to CT in the sense that you have a bunch, you rotate the camera and you measure the radioactivity along the line projecting onto the camera face. Basically, if you can think of the collimators as like a cylinder, so along in that whatever is confined in that straight cylinder is what you typically image. So you do that at every angle, and then you can also once again model the underlying activity as some kind of a line integral. Okay. And you should be able to do this reconstruction very similar to back projection. Okay, the SPECT once again, SPECT imaging geometry we'll see here. With this requires an angle camera that can rotate. One second. So here it's illustrated the angle camera being rotated around the body, acquiring a series of projections, right? So this, if you look at this is a typical camera. It's in 2D. It's like a flat panel, if you can call it that, right? It's a big crystal with bunch of photodiodes behind the crystal. So you will rotate it. So this is the z-axis. Z-axis is always along the body of the patient. Patient is lying down, and you would rotate it along the z-axis, right? And at every point you would collect a series of projections. Very similar to the projections that you acquire using the for X-ray of using an X-ray CT detector. So very similar to that. So you will acquire a bunch of projections here, and after that you have the similar algorithms for reconstruction. So you will have cross sections of radioactivity concentrations being reconstructed. Okay. PET is another radionuclide imaging modality, and positron emitters are used in PET, right? We saw that. So what happens in positron emission is that the emitted positron combines with an electron. So let's say it travels maybe a couple of millimeters in tissue before it is annihilated by an electron, and that annihilation results in the emission of 2 gamma photons, 5 to 11 keV, and these gamma photons travel in opposite directions from the point of emission. Okay. So with 2 angle cameras which are 180 degrees apart, both these photons can be measured simultaneously, can be recorded simultaneously. So how do you know it's simultaneous? So we have a small window, right? So a set of detections you consider to be simultaneous if they fall within a time window of 2 to 20 nanoseconds. Okay. So and this is referred to as annihilation coincidence detection. Usually ACD is the acronym. Okay. See, the coincidence detection means that the annihilation event occurred along the line joining the 2 detecting pixels. Okay. And again similar to SPECT and to X-ray CT, the heads are rotated to collect annihilation data at different angles, and once again there is a tomographic reconstruction formulation. So you get cross sections of the radio tracer activity concentration. Okay. So for instance, here is the PET imaging geometry. So you will have a bunch of you can think of this as the akin to a projection, right? This is the projection. This is the axis along which you have the projection, right? So you have a bunch of detectors, parallel detectors 180 degrees apart, each of them detecting coincidence events along this line. Okay, they will detect coincidence detections along this line, and of course these. So that means that you can actually form a so-called sinogram from these projection measurements, right? So how do you say it's projection? Because any, let's say some the 212 or the 511 keV photons are emitted from this location. So you will have one detection here, another detection there. But if you see, you will see that the this actually travels a certain distance in tissue. This actually travels slightly different distance in tissue, and both of them are attenuated according to the exponential attenuation formulation we had for X-ray photon. So it's the same formulation. And once again, you can cast the problem as in the form of a radon transform and try to reconstruct. Okay, very similar to that. I mean, I'm just giving you a kind of a toy version of this formulation of reconstruction problem. Okay, so the projections are acquired in this way, which is basically you have detectors 180 degrees apart, which detect coincidence events, and then you're rotating along this axis, right? So you'll have a gantry onto which these detectors are set, and then you rotate the gantry and you acquire a bunch of images. Of course, the patient is along the z-axis, the axis of rotation, which is basically, if you can think of it as going into the plane of the screen, the patient bed. Okay, so here are some examples of radionuclide imaging if you have not seen these already. So for instance, on the left is the accumulation of in this case this is positron emission tomography imaging, I believe, and this one is SPECT, right? On the right is SPECT imaging. In this, here there is accumulation of radioactivity in the bone, which you have seen right there, right? I'm not going to do any diagnosis, but I'm just telling you what the images look like. Once again, these images, the images from the SPECT have been superimposed on an anatomical image. I think in this case CT image. Okay. Similarly, the images from SPECT have been superimposed on a on a CT image here. So this is basically the images from the SPECT system. This shows an abnormality in the heart. Okay, and similarly the scintigraphy, right? Here this is dynamic renal scintigraphy. From here you can measure how much each kidney over time. If you measure this, the radioactivity in the kidney, you can figure out how much each kidney is contributing to the bladder output. So these are them are the kidneys, and this is the bladder, right? That's we can measure. Okay, so this is how you see that there is basically no anatomy here, right? It is just a bunch of blobs which indicate the presence of the radio tracer. So the previous images will also look the same, except that they have been superimposed on top of a structural information. So typically there are these PET CT scanners, so called. Now we have, I think, PET MR also. So the PET scanner is used for imaging, for the functional imaging, which is done after the injection of radioactivity, and the CT scanner will be used for getting this for structural information. So they superimpose or fuse both of these reconstructed images, and that's what you will be able to see. Okay, so without that information it will be very difficult to interpret, but an experienced radiologist, nuclear medicine radiologist, will be able to interpret these images. Okay, so where we conclude our review of the common diagnostic imaging or radiological imaging systems. And this idea is to just give you a flavor of the kind of systems available and the kind of images you will run into if you actually do, for instance, a career in medical image analysis or even diagnostic radiology, for instance, with a bunch of images, and you have to understand what these images are. So kind of adds to your domain knowledge. So thank you.